this morning. So Professor Dean Wine is going to talk about the two-dimensional Navier-Stokes equations and the ocean vortex.
So as with previous speakers, I'd like to begin by saying thanks to the organizers for the invitation to participate in this really interesting meeting in this very, very beautiful place. So what I want to discuss today in this first lecture is consideration of a very specific solution of the two-dimensional Navier-Stokes equation known as the ocean vortex. And I'll describe how, using ideas from dynamical systems theory, one can prove that this solution is globally stable in the sense that any initial condition of the Navier-Stokes equation with a two-dimensional Navier-Stokes equation with integrable vorticity will converge to this ocean vortex. And I'd also like to say that all of the work, at least all of that part of today's lecture, which represents my own work, is joint work with Thierry Gallet. And indeed, although my subsequent two lectures won't be devoted so specifically to Thierry's and my work, you'll see that at least the spirit of our very long-term collaboration pervades these lectures. And I'd also like to acknowledge the National Science Foundation for their support of my research. So a theme that I think you've seen emerging in many, many lectures already this week is that when you want to understand long-time fluid motions, it's very often good to begin by looking at some of the coherent structures in the flow. And at least in two-dimensional physical flows, we've seen lots of examples this week that suggest that these structures occur in the form of vortices. And one thing that emerged from Thierry's and my work is that you can sometimes, from a mathematical point of view, view these structures as forming somehow invariant manifolds in the phase space of this system. So I'll focus on two-dimensional fluids, and so those are, from a purely mathematical point of view, an interesting mathematical question. But I want to argue as well that even though we live in a three-dimensional world, there are many physical situations where it really makes sense to think of the fluid you're studying as living in a two-dimensional domain. So, for instance, in the Earth's atmosphere, we've seen some pictures of planetary atmospheres this week. Then there are two sort of dimensions which are two dimensions of the domain of interest are enormously larger than the third. And the third dimension is also small when compared with the typical length scales of interest in the structures under consideration. And so in those circumstances, it often makes sense to approximate the mathematical model by one in a two-dimensional domain. And then, as I say, just from a mathematical point of view, that we'll see there are very interesting differences between two- and three-dimensional flows. So, again, some of these pictures we've already seen this week, but I show them just to reemphasize that if you're looking at two-dimensional flows, very, very often the predominant structures that one sees in the flow occur in the form of very large vortices. So this is a hurricane on the left, and then Jupiter's red spot again. And then finally, the last picture I don't think we've seen yet. These are a satellite picture of clouds downstream from the Aleutian Islands in Alaska. So you can see these very nice vortex streets. So something that was discussed at length yesterday is this apparent tendency in two-dimensional flows for energy to flow from small scales to large scales, so the so-called inverse cascade. And as remarked again yesterday, that's very different from what happens in three dimensions, where energy typically flows from large scales to small scales. But here, at least in these pictures, we see that the typical structures in two-dimensional flows are very large vortices. And so we'd like to discuss how we can characterize these vortices, and in particular, what can we say about their stability. So I'm going to be working in this lecture with the Navier-Stokes equation. And so just to remind everyone, the Navier-Stokes equations for an incompressible fluid describe the evolution of the fluid velocity. And they're essentially Newton's law. So if you look at these equations, the left-hand side is basically just the acceleration of the fluid, and the right-hand side are the forces acting on the fluid. And then the final equation just enforces the incompressibility assumption. And so if you're in d dimensions, then you have actually a d plus one-dimensional system of partial differential equations here. D equations for the components of the velocity field, and then the last equation for the incompressibility condition. One respect in which two dimensions is nice appears when we talk not about the fluid velocity, but about the fluid vorticity. And so recall, again, as has come up this week already, that the vorticity is the curl of the fluid velocity. In principle, the vorticity is a vector. It certainly is a vector in three-dimensional fluids. But again, one of the ways in which two-dimensional fluids are so much nicer mathematically, or one of the reasons, it occurs because if you think about a two-dimensional fluid, that's one in which only the first two components of the velocity of the fluid are non-zero. Then you take the curl, you see that the vorticity in two dimensions has only a single non-zero component. And so we can treat the vorticity of the fluid as a scalar quantity in two dimensions. And that, of course, simplifies the analysis a great deal. We go from studying a system of PDEs to a single scalar equation. So if you take the curl of the Navier-Stokes equations, then in three dimensions, as I say, the vorticity is a vector, and you arrive at this equation right here. Whereas in two dimensions, you get only a single scalar equation. The equations in two and three dimensions are similar, but of course there's this term in the three-dimensional equations that's missing in the two-dimensional equation. That's kind of the million-dollar term. It's known as the Vortex Stretching term. It sort of has the sort of physical property that, at least in certain configurations, it can provide a sort of feedback mechanism whereby the vorticity is sort of self-reinforcing, and at least in principle, the vorticity might become infinite. And that's, of course, why, or it's the presence of this term that has so far prevented a proof of the sort of global well-posedness of the three-dimensional Navier-Stokes equations, which is one of the famous Millennium Prize problems. So, however, things are much nicer in two dimensions, and that's where I'll restrict attention to in this lecture. So, in fact, the existence theory for the two-dimensional vorticity equation is quite straightforward, and one can even prove existence and uniqueness of solutions for initial vorticity distributions which have very little, if any, regularity, say initial vorticity distributions containing distributions. But if you just step back from the equation and look at it for a minute, then there's at first glance a complication, and that is that it doesn't look like these equations are closed. The velocity of the fluid is still appearing in the equation for the vorticity, and so it's not immediately clear how to cover the velocity field. But in fact, if you think for a minute, then if you recall two facts: one, that the velocity is assumed to be incompressible, and two, that the vorticity is just given by the curl of the velocity field, then indeed you remember that you can recover the velocity field via the Biot-Savart operator, and so that's a linear but non-local function of the vorticity. And so you can think of this term, think of the velocity as being B of omega, where B is just the Biot-Savart operator. And so we can think of this equation as a perturbation of the heat equation, where we have here a quadratic but non-local nonlinear term. And so that's the point of view that I'll sort of emphasize in this lecture. We want to think of the vorticity equation as a kind of nonlinear heat equation. That turns out to be a very, very fruitful point of view. So again, these pictures are numerical simulations of the two-dimensional Navier-Stokes equation. This comes from the web page of the Fluid Mechanics Lab at the Technical University in Eindhoven. And we've, again, seen very similar simulations in talks earlier this week. But just to reiterate, the sort of very interesting phenomena, the very typical phenomenon for two-dimensional flows is that we have this sort of coalescence in which a very large number of small vortices progressively simplifies until you reach a state where you have just a very small number of rather large vortices. Okay? And so we'd like to understand this process. So there's this nice poem I found on the internet. So when little whirls meet little whirls, they show us strong affection, elope, and form a bigger whirl, and so on by advection. Okay, so that's our goal, is to understand this poem here. So, okay, so as I said, so we have the two-dimensional vorticity equation, and I'm going to talk a little bit about two sort of very complementary limits of the equation. One in which we assume the viscosity is small. The viscosity parameter is the parameter nu in the equation. Assume that's small and just consider this kind of advection equation where the vorticity is just advected by the velocity. But, of course, that's not quite true because the velocity is itself determined by the vorticity. So there's a certain feedback here. And the second limiting case is when we ignore the nonlinear term and just think of this somehow as a perturbation of the heat equation. Now, if you ignore the viscosity, then, of course, more than 100 years ago, Helmholtz and Kirchhoff suggested that it might be a good idea, or at least under certain circumstances, a good approximation to study the limit in which the vorticity distribution can be regarded as just a sum of isolated point vortices. And so as I said, in this case where you ignore the viscosity, then these vortices are sort of advected or swept along by the velocity field, which is itself created by all the other vortices. And so you have this sort of complicated interaction. But what Helmholtz and Kirchhoff realized is that you could represent the motion of the centers of the vortices just by this simple system of ordinary differential equations. And it turns out that this is again, as has been noted already this week, a Hamiltonian system of differential equations. And I'll come back and talk about how one can use ideas from celestial mechanics to investigate certain special solutions of this system of equations in my third lecture on Friday. But I'll talk for just a minute, and a very brief minute, because this was described so beautifully yesterday in Professor Dritschel's lecture, about a much more recent idea about the point vortex equations, which goes back to Onsager, who suggested that since this is a Hamiltonian system of equations, if we have a large number of vortices, and we assume that they're moving about in a chaotic fashion, then Onsager noted, again, as was explained yesterday, that one got these peculiar states of negative absolute temperature, and that he interpreted this as meaning somehow that vortices of like sign would try to clump together. And this was, as explained yesterday, his proposal for understanding the growth of large vortices in two-dimensional fluids. Now, as pointed out also yesterday, there are a number of drawbacks about Onsager's proposal, not least the fact that we don't really know if the underlying dynamics obeys any of the hypotheses of assumed by when you start to study statistical mechanics. But this was at least one sort of very appealing physical idea explaining the origin of some of these large vortical structures. But let's turn from that for a moment and look at sort of the other limit, where we ignore entirely the nonlinear terms in the equation and just think about the heat equation limit. Well, in this case, if you assume that you start with an initial condition that is a single point vortex, that is to say that if you assume that the initial value of the solution is just a constant times the delta function, then of course you can solve the heat equation with that initial condition, and you get this very simple form for the solution at later times. And the kind of remarkable fact is that this solution is not only a solution of the heat equation, but also a solution of the two-dimensional Navier-Stokes equation. And this has, of course, been known for a very long time. The solution is known as the Osane-Lamb vortex. And it comes about, the fact that it's a solution of the two-dimensional Navier-Stokes equation can be seen immediately from the Biot-Savart law. If you think about the Biot-Savart law, since the vorticity distribution is a purely radial function, it depends only on the modulus of the spatial variable, then the velocity field corresponds to this vorticity distribution will be purely tangential, and therefore the nonlinear term in the vorticity equation will vanish identically, okay, because of the dot product. And so this solution will satisfy not just the heat equation, but also the vorticity equation. Now, this is kind of reminiscent of these numerical simulations I showed you earlier, because note that in the Osane-Lamb vortex, or the fundamental solution of the heat equation, the spatial scale is growing with time. Okay, the length scale over which the sort of core of the vortex extends grows with time in a linear fashion, and we see that something similar appears to be happening in these numerical experiments. So the size of the region over which the vorticity extends is increasing with time. And that suggests that maybe it would be profitable to study the equation in variables that take that effect into account. And so we'll introduce into the vorticity equation so-called scaling variables. So we'll replace the spatial variable x in the equation by this new variable xi, which is rescaled by 1 over square root of t, or just to avoid the singularity at t equals 0, 1 over the square root of 1 plus t. And hopefully that will capture somehow in a natural way this growth of the solution, or growth in the length scale in the solution as a function of time. And we also, for reasons that are maybe a little less apparent, rescale the time variable. We introduce a new time variable tau, which is just the logarithm of t. So if we introduce those variables, and so we'll introduce, we'll rescale the vorticity as well. So we'll introduce a new dependent variable w to replace omega. And this rescaling is again chosen just to mimic the scaling that we observe in the fundamental solution of the heat equation. Namely, there's this factor of 1 over t in front of the solution, which we, so to speak, put in by hand here. And we'll rescale the velocity in an analogous fashion. So if we make that rescaling, then the vorticity equation takes this form, okay? And there's a typo here. This should be v. I'll call the rescaled velocity v rather than u. And at first sight, it looks like we've made things worse, okay? Remember, in our original variables, the vorticity equation was just dw by dt, or d omega by dt, is Laplacian of omega minus this quadratic term. And now we've replaced the Laplacian by this sort of rather more complicated linear operator. But this rewriting of the vorticity equation in terms of the scaling variables has a number of advantages. First of all, the first advantage is that the Osane vortices are now just fixed points of this equation. So instead of looking at a family of self-similar solutions, we're looking at a family of fixed points. And if you're thinking about this problem from a dynamical system point of view, that's actually a good thing. We have lots of dynamical systems techniques for studying fixed points. The other fact has to do with the spectrum of this operator L. And so now I have to talk just a little bit about function spaces. So I'll discuss this at much greater length in my lecture tomorrow. But for today, I'll just remark that it's been known for a long time that if you're studying parabolic equations, then spatial and temporal decay are often somehow intertwined. And so we'll look at this operator in a set of weighted L2 spaces. So I'll define a space L2 of M, which are just square integrable functions the integral of whose square is finite also when weighted by this polynomial weight growing like c to the m at infinity. So these are spaces of functions that have a certain imposed decay rate at infinity. And it turns out that, again, I'll explain this in greater detail tomorrow, that in these spaces you can compute explicitly the spectrum of the operator L. There's a sequence of eigenvalues that occur at all non-positive half integers, 0, -1/2, -1, and so on and so forth. And then a sort of half plane of essential spectrum, so everything to the left of this line is in the spectrum. But it turns out that we can push that essential spectrum far into the left half plane by choosing the weight in our function space appropriately. So the faster the decay rate of the functions at infinity, the further into the left half plane the essential spectrum is pushed. And so the long-time behavior of the solution, at least intuitively, ought to really be governed by the behavior associated with these eigenspaces of this discrete set of eigenvalues. So, and again, as I say, I'll explain in greater detail how this sort of form of the spectrum arises tomorrow. But for today, I want to just focus on the Osane vortices and show you that, in fact, these vortex solutions are globally stable. So there are, of course, again, at least a couple, if you're thinking about this problem from a dynamical systems point of view, there are at least two natural ways to think about proving stability of some fixed point. You could take a local approach, which is based on the linearization about the fixed point. And, of course, now that we understand the behavior of the spectrum of L, we have a good start on that approach. But today I want to focus on the second, more global approach based on Lyapunov functionals. Because as we'll see, there are two actually rather simple and natural Lyapunov functionals that apply to the two-dimensional vorticity equation that allow us to demonstrate that these vortex solutions are globally stable. So just this is something I think maybe hasn't been discussed so much this week. So I'll remind you what a Lyapunov function is. So we'll look for a function of the vorticity field that is a monotonic, non-increasing function of time. And we'll use it to describe the omega limit set of the solution. So remember, or if you've heard of it before, remember, and if not, let me explain to you what the omega limit set is. So the omega limit set is a set associated with certain solutions of an equation, describes the long-time behavior of those solutions. The omega limit set can be a fixed point, it can be a periodic orbit, or even so some chaotic attractor. And every orbit will have an omega limit set provided it satisfies certain compactness properties. And so that's one situation where, or one place where the situation is a little bit different if you're dealing with partial differential equations as opposed to ordinary differential equations. The compactness kind of comes for free in the ODE case whenever you can prove that the solutions are bounded, and it often requires a sort of an additional step when you're dealing with PDEs. So here's the formal definition of the omega limit set. Basically, the omega limit set associated to an orbit is a set of points such that the orbit gets arbitrarily close to it arbitrarily often. And so that's encapsulated in all these words, which I won't read to you. But the idea is just that we want to look at the set of points such that the forward orbit of some given point, W0, gets closer and closer to this set of points as t goes to infinity. And as I said, it's possible that the omega limit set is empty, but if you know something about the compactness properties of the forward orbit, then you're guaranteed that it'll always contain at least one point. Now, the sort of key fact that makes it possible to pin down the omega limit set with the aid of Lyapunov functionals is known as the LaSalle invariance principle. And basically that says that if you have a Lyapunov functional for your system, the only possible candidates for points in the omega limit set are the part of the phase space of your system where the Lyapunov functional is constant when evaluated along an orbit. And so, more precisely, suppose H is a Lyapunov functional for your system, then the only candidates for points in the omega limit set are points at which the derivative of H along an orbit is 0. So the Lyapunov function has to be constant along points on the orbit in order for that point to be in the omega limit set. So that's the tool that we'll use to pin down the location of the omega limit set. So as I said, there actually requires using two Lyapunov functionals, or our argument, Galet's and my argument requires using two Lyapunov functionals. One of them is kind of, you can think of, although I have to say this maybe came a posteriori, you can kind of think of it as related to Onsager's idea in that we use a Lyapunov functional that's based on the entropy, okay? And then the second Lyapunov functional is based on this analogy with the heat equation because it really comes from the fact that, like the heat equation, the vorticity equation satisfies a maximum principle. So let's look first at the Lyapunov functional based on the entropy. So again, as we heard yesterday, the entropy is just the integral of W log W. Now, if we take W to be the vorticity of our fluid, then since we're on an unbounded domain, that integral will typically be infinite. And so we'll study what's known in kinetic theory as the relative entropy, where we look at the entropy of W compared to some given solution. And in our case, we'll just take the given solution to be the Gaussian vortex. So here, G of C is just e to the minus c squared over 4, or maybe 1 over 2 pi times e to the minus c squared over 4. And so we'll define this function to be our relative entropy. And what I'll show in subsequent transparency is that indeed this function is monotonic, non-increasing along solutions of the two-dimensional vorticity equation. But there is a problem with using this as a Lyapunov functional for the vorticity equation. As I said, this was developed in kinetic theory, where if you think about it, you have a kind of similar question. Again, in kinetic theory, you often want to show that solutions of some kinetic equation are converging towards a Maxwellian, so a Gaussian distribution, just like we have here. And so that's kind of natural that this tool might be applicable in these circumstances. But in the kinetic theory case, the dependent variable is usually a probability distribution. And so it's very natural to assume that the dependent variable is positive. That's not at all natural to consider only positive vorticity distributions. But our relative entropy functional is only defined for positive solutions W. Or you can define it for negative solutions equally easily, but there's no natural way to define it for solutions that change sign. And those are, of course, the most common and interesting solutions for the vorticity equation. And so we'll use this vorticity equation, but you should keep in your mind that that it has a very significant limitation, and that is that it's not really defined for the solutions for many solutions of interest. Okay. However, if W is defined, then if W is non-negative, then we can show that. Sorry, it should be strictly positive. Then we can show that the relative entropy is defined and continuous and actually bounded from below on these weighted L2 spaces, at least when the weight function m is greater than 3. And I'll come back to relaxing this requirement a little later. But for the moment, let's just assume that we're going to consider the relative entropy function on this space of positive, somewhat rapidly decaying solutions of the vorticity equation. Then one can also show that for initial conditions in this set sigma plus, the forward orbit is relatively compact. And that depends on just two facts. One is some smoothing properties of the semigroup, and then some localization of the solution. The fact that you can show that the solution actually decays a little bit faster in space, up to a piece that goes to 0. And these are basically just kind of hands-on estimates of the integral form of the vorticity equation. Yes, sorry. Yeah, so I'll come back to that in just a moment, but that's absolutely crucial for us. And it's a consequence of the maximum principle. So we have a maximum principle here. And yeah, so that's a good remark. In fact, if the vorticity is initially just non-negative, it will be strictly positive at any positive time because of this maximum principle. And so now that we know that this function is well defined, we can ask, how does it evolve? And so if you just take the derivative of the relative entropy, you by a very simple calculation, find that the derivative can be written as just 1 plus the natural logarithm of W over G times this linear operator times W, and then minus a term involving the nonlinear term in the equation. Now, if you first study the linear piece and just integrate by parts a lot, then you find that this integral is just minus W times the square of the gradient of W over G. Okay? A little bit more interesting is maybe the nonlinear term. So if you can start out by rewriting the nonlinear term as instead of V dot gradient W as just the divergence of V times W. So this step depends on the fact that we're looking at incompressible flows. And then you integrate by parts, and so you get these two terms. And now it turns out that just by relatively straightforward calculations, each of these terms vanishes. So I won't go through the details there. But what we see then is that the only contribution to the time derivative of the relative entropy is this integral that comes from the linear term in the equation. And if we now think of this formula in light of the LaSalle invariance principle, we immediately learn two things. First of all, clearly the right-hand side is less than or equal to 0. So this is a Lyapunov functional. And secondly, now think about the LaSalle invariance principle. The LaSalle invariance principle says the only possible candidates for the omega limit set are the points where the derivative of the Lyapunov functional are 0. And since W is assumed to be positive, the only way this integral can be 0 is if this term vanishes, and the only way that can happen is if W is a constant multiple of the vortex solution. And so if we restrict our attention to positive solutions of the vorticity equation, then the only candidates for the omega limit set are multiples of Hossein vortices. And so so that's very encouraging. But as I said, of course, looking at solutions in which the vorticity has only one sign is, at first glance, not a very interesting set of solutions for the vorticity equation. So what do we do with solutions that change sign? And as I say, here we really live from the fact that, like the heat equation, the vorticity equation satisfies a maximum principle, which implies, in particular, that if our solution is positive at some time t naught, it will remain positive for all later times, and that, in fact, the initial value of the solution is just non-negative. It will actually be strictly positive at all subsequent times. Okay? And these, you can check these two facts also hold when we re-express the equation in terms of the rescaled variables. And it turns out that with these two observations, then we get a second remarkably simple Lyapunov functional. Namely, it turns out the L1 norm of the solution is a Lyapunov functional. And again, I can sort of prove that for you in more or less one transparency. We begin by writing the vorticity as a difference between two pieces W1 and W2, where W1 and W2 satisfy these things that are very like the vorticity equation. The only difference from the original vorticity equation is that the velocity field that occurs in the advection term is really the velocity term field for the full solution. Okay, so that's the only respect in which these are not the original vorticity equation. And as initial conditions for W1 and W2, we take respectively the positive and negative parts of the initial vorticity distribution. Okay? So note that this is not saying that W1 and W2 are the positive and negative parts of W of t, but they're solutions of these equations that come from the positive and negative parts of the initial data. And again, the fact that I'll use on the next transparency is that both of these equations, the equations for W1 and W2, satisfy the same maximum principle that the solutions of the vorticity equation itself satisfy. And so now we're in business. Because suppose you compute the L1 norm of W at time tau. So certainly that's less than or equal to just the sum of the two parts W1 and W2. Because the maximum principle guarantees that since the initial conditions for W1 and W2 are non-negative, the solutions W1 and W2 at any subsequent time will be strictly positive. So we have this inequality. Now, the other fact that you can easily check is that these equations, and this depends on the fact that V is incompressible again, these equations can conserve total vorticity. So the integral of W1 at any time tau will be equal to the integral of the initial condition for W1, and likewise for W2. So this integral will just be the integral of the sum of W1, 0 and W2, 0. But again, W1, 0 and W2, 0 were just the positive and negative parts of the initial vorticity, and so this will be equal to the L1 norm of the initial vorticity. And so we see that the L1 norm of the vorticity is less than or equal to the L1 norm of the initial vorticity. Okay, so the L1 norm is a Lyapunov functional. Now, let's think about the LaSalle principle. Now that we know that it's a Lyapunov functional, what's the LaSalle principle say? Well, it says that this the only possible candidates for points in the omega limit set are points where the Lyapunov functional is constant along orbits. So the only inequality is this one right here. And when could we have equality in this relationship? Well, again, as a consequence of the maximum principle, recall that I said that if the initial condition for W1, 0 and W2, 0 is greater than or equal to 0, the solution will be strictly positive at all subsequent times unless the initial data happen to be identically 0. So unless either W1 or W2 is 0, there will be a strict inequality here because we'll have some cancellation between W1 and W2, when we replace the absolute value by the sum of these two terms. And so the only set of solutions for which this Lyapunov functional is constant are the set of solutions that are either everywhere positive or everywhere negative. And so by the LaSalle invariance principle, the only possible candidates for solutions or the only possible candidates for points in the omega limit set are solutions that don't change sign. Okay, and so if we put those two observations together, so we've just seen from the Lyapunov functional given by the L1 norm that the only candidates for the omega limit set are solutions that are either everywhere positive or everywhere negative. And on the other hand, for any such solution, namely any solution that's everywhere positive or everywhere negative, the relative entropy functional tells us that the solution, or the omega limit set, must be a multiple of the Osane vortex. And so what we see is that at least if we restrict ourselves to these solutions that decay relatively rapidly, any such solution must decay to an Osane vortex. Okay. I've left out one qualifier here. I've sort of assumed these equations all conserve total vorticity, or circulation, if you like. So I'm assuming we have non-zero circulation. Otherwise, you could converge to the zero solution. Okay, but aside from that, that's the only qualifier I've really omitted. So we know that the omega limit set is non-zero, and the only possible point in the omega limit set is a multiple of the Osane vortex. And it can't be more than one multiple because of the conservation of circulation. And so that's how we, so I left out that last step. So. Okay, so how do we extend this to all of L1? So this is, we begin by showing, first of all, that the forward orbit is relatively compact because we need to know that the omega limit set exists. And this actually goes back to spatial decay estimates due to Carlin and Loss. And so, in fact, what you can show is not only is the forward orbit relatively compact, that in fact you can show that the omega limit set must be in L2 of M. And then you can then apply the previous argument. Once you know the omega limit set is in this set, then we know that the omega limit set of any trajectory in L2 of M is the Osane vortex. So we find then that if you take any solution of the vorticity equation whose initial vorticity is integrable and which has non-zero total circulation, then that will tend, as time goes to infinity, toward the Osane vortex with the same circulation. So let me now just say a little bit about possible extensions. First of all, the first remark is we don't really get, unfortunately, one drawback of these arguments with the Lyapunov functionals is that we don't get a very good estimate of how long the convergence takes. So lots of interesting things may, and in fact, as we've seen from sort of numerical simulations and some of the earlier lectures in this conference, interesting things happen in the fluid before this sort of long-term asymptotic state appears. And so we'd like to better understand these types of behaviors that manifest themselves prior to the appearance of the Osane vortex. So, of course, again, one thing that we saw yesterday that's very important and I think not very well understood mathematically is this process of vortex merger. So somehow, from the numerics, it's clear that two little vortices get close to each other and they undergo this complicated dance and eventually become sort of one. So we don't really, unfortunately, our proof doesn't really give any insight into how this process occurs. So that's one thing that would certainly be nice to understand better. And here's a very beautiful actual experimental picture of this process. So you can see that somehow the Osane vortex is capturing sort of the dissipative parts of the evolution, but clearly this process of vortex merger has to include the very complicated nonlinear sort of intertwining that happens when vortices merge. Another phenomenon is metastability. So this refers to the fact that there are sort of typical sort of structures that occur in the flow before you reach the sort of dissipative limit, the Osane vortex in this case. And while those are not so well understood in the Navier-Stokes equation, Margaret Beck, a colleague of mine at Boston University, and I were able to use dynamical systems ideas to explain this metastable phenomena in Berger's equation, which is a kind of testing ground often for trying to understand the Navier-Stokes equation. And so what we show there is that just as in Navier-Stokes, Berger's equation has a family of self-similar solutions that are the long-time dissipative limit of the solution. So these are sort of well-known solutions of self-similar form for Berger's equation. You can show that all solutions tend to one of those self-similar states, just as in Navier-Stokes we showed that all solutions eventually tend to an Osane vortex. But in Berger's equation, one can do a little better. Namely, you can show that through each of these asymptotic states, there's a one-dimensional attractive invariant manifold. So what we show is that almost every initial condition will undergo a relatively short transient where it approaches some neighborhood of one of these attractive invariant manifolds. And then since they're attractive, once it gets close to that manifold, it will stay close to that manifold forever. And so its subsequent evolution is really governed by what happens on this invariant manifold, which it turns out in the Berger's case you can describe quite explicitly via the Kohl-Hopf transformation. And so we'd like to argue that somehow one might find a similar explanation for the metastable behavior in the two-dimensional Navier-Stokes equation. So just to sum up, this first lecture, I'd like to say that while this isn't really any justification of Onsager's prediction, we can use these Lyapunov functionals and very simple ideas from dynamical systems theory to at least show that in the very long time limit, every solution of the 2D Navier-Stokes equation with integrable initial vorticity will approach this very explicit vortex solution of the equation. So thank you very much.